welcome on this California day in the middle of October. Hope you'll apologize for short sleeves. And commenting on the last session is, a reason to get a PhD is, in your 20s, it's a pretty great way to get a background that prepare you for the rest of your life. And I don't know that people who got a PhD who thought they wasted that time, especially in these fast-moving days. So what I wanted to point out, our Turing celebration that we're having right now at Berkeley. It started a couple of weeks ago, and it's going to last for the next several weeks. But remarkably, like Chuck said, Berkeley is where Turing Award research is done. There's 7 awards of the 51 awards totally given. 7 of them were done on research based on Berkeley, and we're having 2 people share the award, but we're having the 8 speakers there. So to put this in perspective, how many is 7? So MIT plus Stanford are kind of well-known rivals. They have 7. Berkeley has 7. So go Bears. All right. So this is. How many of you have a pretty good computer background? Let me just check. Okay. All right. We'll see how this goes. All right. So we're going to do 50 years of computer design in 10 minutes. But there's going to be 3 lessons from that probably anybody can understand, which is that, I'm going to be talking about hardware, but advances in software can inspire hardware ideas. The second point is kind of I'll talk about software going at a higher level, so kind of raising the level of abstraction, we call it, and that lets innovation. And then finally, because computer design is tied to this commercial world, we have these arguments in other fields that they try and settle in debates and things like this. In computer architecture, it involves billions of dollars invested in computer design, and we kind of fight it out in the marketplace. All right, so I'm going to give you the 50, let's go back 50 years to the problem that IBM had. Whoops. So IBM had what was, in the early 1960s, 4 independent lines of computers. Now, when software talks to hardware, there's a vocabulary. So for the hardware to understand its vocabulary, that's called an instruction set. And the words of the vocabulary are called instructions. So they had 4 different computer lines with 4 different vocabularies or 4 different instruction sets. So that meant the software was different in all 4 lines. It had 4 different market niches. They were all incompatible. So some IBM engineers had this radical idea, that we could have one vocabulary for the next generation hardware that bring all 4 of these lines together. Now, Now, it turns out there's 2 parts to any kind of processor or computer. There's the brawn, the part that does the work, like computing arithmetic, and there's the brain that tells it what to do. So the brawn's called the data path, and the brain's called control. So the hard part of designing a computer is the brain part, is the control. So IBM had to convince these 4 independent pieces of the company that they could all do the same vocabulary, so they needed an idea how to do that. So they went back to the person who won the second Turing Award. He had an idea how to do it, which was inspired by software. And what his idea is, you could specify control as a 2-dimensional array with the columns being control lines and the values going into the control lines. The rows of that array he called a micro instruction. And so then you could program the control like it's software. That was his idea. And he called that microprogramming. So IBM decided to do that, and in April of 1964, they made the biggest announcement in the history of the company. They bet the future of the company that they could make this single vocabulary work across all these lines. And that single day, they announced 4 different lines of computers. They varied in speed, and they varied in cost. And what happened is IBM won that bet. IBM announced that family of computers, a brand new idea, and then they dominated the industry for the next many decades. And in fact, a descendant of that computer, here it is 55 years later, even today is a $10 billion a year industry. And one of the people who made that happen, the person who was in charge of that project, is another Turing Award winner from IBM, Fred Brooks. All right, so the next, let's fast forward to like 10 years, and there's another part of a computer industry. Before we were building computers, we weren't really using integrated circuits, and now we are going to start using integrated circuits. And so with the integrated circuits, and that we're building the control memory out of integrated circuits, there's this thing called Moore's Law, which everybody's heard of. And Moore's Law, when it's integrated circuits, kind of every year the technology gets better. So what that meant was we could have bigger control stores, which meant we could have a more complicated vocabulary. And this computer was a good example of that. Oops, keep going the wrong way. So then along come microprocessors. Now the microprocessors, largely centered here in Silicon Valley, they weren't very good at computer design. They would just imitate what the big computer guys did. That was the way they did it. So they would compete with each other by writing at a very low level, very tedious level, because the microprocessors were pretty wimpy. They would add instructions, add to that vocabulary with kind of unusual things and show that it would work, but it was very tedious to program in these. Now, what happened, Gordon Moore, the person for whom Moore's Law is named, was a visionary. And at the time, Intel had what was called an 8-bit computer, a very simple computer. He thought the next vocabulary that they invented, the next instructions that they invented, would last the lifetime of Intel. So what he decided to do was to hire a bunch of computer science PhDs, send them from Silicon Valley up to Portland, Oregon, and to invent the next great vocabulary, the next great instruction set. And so they had free rein, and they came up with all kinds of complicated ideas. Unfortunately, it had severe performance problems, and it was late. So they had to go back to Gordon Moore and said, you sent us up to Oregon to invent the next great instruction set, but we're not going to have it in time. So Gordon Moore at Intel forced to do an emergency project to come up with a vocabulary for a 16-bit processor that they could do in time, and they called it the 886. They were given 52 weeks to do everything, design the vocabulary, design the chips, and all that stuff. So they were only able to spend 3 weeks on the vocabulary, and they finished it up, and they announced it, but there was not much fanfare. So, okay, Intel has a 16-bit one, but there wasn't a lot of excitement. To their tremendous fortune, IBM decided to get into the personal computer market to compete with the Apple, which was dominating the personal computer market, and they needed a microprocessor, a 16-bit microprocessor. So they liked one from a competitor from Motorola that was kind of like the vocabulary of the IBM 360 one, the one I told you about earlier, but it was late. So they had to go with this emergency replacement one, the 8086. So what happened? Well, the estimated sales over the next 5 years was going to be 250,000, which is okay for microprocessors, no big deal. But they were wrong. Instead, it was 100 million. So Intel had the emergency vocabulary that Gordon Moore knew they had to get out. It wasn't the one that the PhDs came up with, it was the emergency replacement, but it became the dominant one. All PCs in the world use this, and all PC software was written for these. Okay. Now this kind of style of computer that had this control store with microprograms in it, people started taking a look at those things and do some technical analysis. So the first one is another Turing Award winner, John Koch of IBM, and he built a simpler vocabulary in a piece of software that's called a compiler. So what a compiler does is translate from one language to another. So a compiler will translate from a language that's much easier for humans to understand into the language that computers can understand. So it raised the level of abstraction. So the question, and you could think of, so what's a compiler? You think of like translating from English to Chinese. If you had an interpreter there, it'd be kind of slow, but if you translated it in fast, you could read it fast. So compilers do things offline really fast. So the question was, well, let's take a look and suppose we use the simple version of the IBM 360 vocabulary, don't use the complicated ones, what would happen? And what they found is it ran up to 3 times faster by using the simpler stuff. So that's the surprise. So they left stuff out and it ran faster. And then at the place that did the other kind of, the mini computer company, they took a look at their design and found out that most of that control store, most of the microprogram was unused, hardly ever used. So that kind of called into question of these things. And that's this translation from what's called the complex instruction set computers. So those are the older vocabularies with lots of complicated instructions to what's called the reduced instruction set computer. As you can, from the words, it's a vocabulary with simpler instructions. So you know, kind of $5 words in the other one, and real simple monosyllabic words in the other one. So, okay, let me. So the instruction set is simple, like I said. They're as simple as those micro instructions. And there's a thing called pipelining. It's kind of like the way you build a car. You put it into a manufacturing process, sorry, and each step of the line, and then you can get more cars out of the manufacturing. Same things works with computers. It's a pipeline execution, much more efficient. And the complicated instructions weren't used all that much anyways. And there were some new algorithms that could allow this simpler one to be used much more efficiently. And then it came time to explain it. And I'll just kind of explain it informally, but that formula is what it's part. So the question was, if we have a complex vocabulary and a simple vocabulary, you would think that when you run a program with a complicated one, it would take fewer instructions. And it would. It would take fewer instructions. But the question was, if the words were really complicated versus the simple ones, you'd think you could read the simpler ones faster. So read the simple ones faster, but you don't have to read as many of the complicated ones. So the question is, what were those numbers turned out to be? Well, it turned out you'd only had to read about 25% more instructions if they were simple, but you could read them about 5 times faster. So that meant the net effect, you read more of them, but they go 5 times faster. It ended up to being about 4 times faster. So that was the argument for RISC. And that's what's on this slide. Now, at the time, that formula wasn't in textbooks of the time. And so John Hennessy and I decided to write a textbook that had that characteristic to it, and that's the book that Robert talked about. And it's hard to describe before then, but basically the computer textbooks at the time would be kind of like a catalog. It'd say, well, this computer has all these features, this computer has all those features, and it would just kind of list all the features that they had. And it was hard to figure out, well, why was one better than the other? So this quantitative approach that Hennessy and I did tried to give a bunch of formulas and rules so that you could evaluate designs before you did them. So that was a different way of doing it. Okay. Now here's where we had these ideas, but in computer design, you build hardware. Hardware is kind of the proof is in the pudding. Hardware, we'll see what the truth is. And so the first one, which was done at Berkeley, is called RISC-V. That was done in classes here. And there was a follow-on one called RISC-II that was more efficient. And then at the same time, our colleagues at Stanford, led by John Hennessy, did a MIPS design. And so I can still remember kind of the leading conference. This was, I guess 35 years ago, where these two designs were presented. And they were done by a handful of graduate students at Berkeley and another microprocessor by a handful of graduate students at Stanford. And once they were presented in this auditorium with, thousands of people in it, there'd be this mumbling in the audience. The audience would start talking to each other because it was such a stunning result. And it was a remarkable moment in time where graduate students could build microprocessors that were arguably better than what industry could build. So that inspired people to build commercial versions of these ideas. But Intel, which had the emergency instruction set, didn't take this lying down. What they decided to do is put really big teams together, and they actually, in hardware, would translate from the older vocabulary internally to a RISC vocabulary. So in hardware, they did that translation, and then anything that they wanted to, any good idea the RISC ideas had, they could do in the CISC architecture. So they would internally do that translation, and they had much better technology to be able to do that. And so they were eventually able to dominate, and because the PCs were cheaper, they were also less expensive. So they eventually dominate the PCs. But that's the PC era. We are, as Chuck said, in the post-PC era with the iPhone in 2007. And now it's not just performance, but energy efficiency matters as well. So the efficiency of RISC, again, is working well in this post-PC world with all the phones devices, embedded devices. And so there were 20 billion last year chips with RISC, with processors in them, and like Chuck said, 99% of RISC. Okay, so that's 50 years of computer architecture in about 10 minutes. And again, the marketplace settled that, is RISC was winning the post-PC era, and that CISC ended up winning the end of the PC era. So what are some of the challenges going forward? So you've all heard of Moore's Law, and it's been around for more than 50 years, except it's over now. So Moore's Law is the blue line at the top, and the red line is showing that we're off about a factor of 15. We're not doubling the number of transistors every 2 years, as Moore originally predicted, and was true for decades. So that's a big deal for computer designers. Another one that's no one knows about is called Dennard scaling. And you kind of wonder, how could you keep doubling the number of transistors in the chip? Wouldn't it get so hot? Well, Dennard noticed what we would do is what's called lower the threshold voltage. And so every area of the chip would end up using about the same power, even though it had more transistors in it, which was a remarkable thing, and that was true for decades. Well, that stopped being true. So what that means is, and this is from the first figure of our textbook, is there was a time, you know, over 15 years, where computers doubled in performance every 18 months. And what people would do is throw away perfectly good computers on their desktop because their friend's computer, which was 2 years newer, was a lot faster. So you just throw working computers away because it felt slow. Now, these days, we are long past that, as you can see with the things I talked about. Performance hardly improves at all, just a few % per year, so nobody throws their laptop away because their friend has one that's a year or two newer. They're about the same speed, so we've lost that performance advantage. So now what the opportunities are left is both in the software side and the hardware side, and then we'll do it together. So I'll talk about one example. So, okay. So how many of you know what Python is? How many of you know Python? Oh, great. All right, so Python is really a very cool language. It makes you very productive, but it's pretty slow. So how slow is it? So this slide shows that. So we're talking about a simple operation, matrix multiply. If you write it in Python, suppose you rewrite it in a lower level language, C. How many of you know C? Okay, all right. So this is why you learn C. So it goes about 50 times faster, just rewriting from Python to C. Then the next question is, modern computers have lots of processors on them. They're so-called multi-core. So the software can't figure it out yourself, but you can go in there and identify the explicit parallelism, and you can get it go another, I think it's 10 times faster? Yeah, or 9 times faster, just identifying the parallelism. But then modern computers have elaborate mechanisms called caches, and these are just small flash buffers that have recently executed instructions, because you're probably going to use them again. If you take advantage of the caches, you can get a factor 20 in advantage, and then modern microprocessors have special instructions that can do many operations at once, called SIMD. Take advantage of that. So if you multiply all those things together, you can go a factor of 63,000 times faster than writing it in plain Python. Okay, so that's amazingly slow. If you go from C++ and you try and optimize that software, you're a hero if you can get a factor too. There's a factor of 63,000 sitting here on the table. So here's this opportunity, if you want to go get a PhD in computer science, to get a Turing Award for speeding up Python. Okay, it's amazing how fast it is. Okay, now. Okay. Now, the other thing, we can't make, you saw that slide, that general purpose microprocessors aren't getting any faster, so what are we left? What we do instead is to make microprocessors that only do some domains really well, and those can go a lot faster. The one that we're going to speed up, what should we use these special purpose microprocessors for? Well, here's a field where the number of papers increases by Moore's law, okay? And that's machine learning. So let's try and speed up machine learning. So this is an example of one that was done at Google. It was done in 2015, and it's The leading professional association, ACM, this flagship magazine, it's on the cover. And I'll show you that. But if you use Google, you've been using TPUs. That gets used routinely. The main thing on this slide that I want to tell you is the number of arithmetic units, the multiply accumulate units. Kind of remarkably, this has 65,000 arithmetic units on it. So by narrowing the application area, you can throw a lot of stuff out and reuse those resources for something that's really important. So how many of these 65,000? That's like 100 times more than modern microprocessors. So in terms of the performance consequence of that means that compared to CPUs, it runs 80 times, it runs, in terms of through the performance per watt, which is important in these energy limited days, it runs 80 times faster and about 30 times faster than GPUs. This was done using Google's production workloads. There's an effort that's going underway right now to do benchmarking that everybody can run, and that's going to be really interesting to be able to see fair comparisons against all these hardware devices. All right. Right now, there's kind of it's a Cambrian explosion of architectures going on. NVIDIA is making a particular bet in computer design. Google's making a different bet. Microsoft's making a different bet. And then Intel's betting on all of them, basically, covering all the bets. But we're seeing, and then there's 45 startup companies that have their own bets in this area. So we're seeing a tremendous innovation, and we'll see what happens. And you don't know who's going to win, but you know the marketplace is probably going to sort that out. And then the last thing I'm going to tell you about is open source hardware. So we've heard of open source software, operating systems like Linux and compilers and things like that. How come that's not true for hardware? So to tie this back in, this is where RISC-V comes in. So in 2010, we needed to one of these vocabularies for our research project. The leading obvious ones, the proprietary ones, one from ARM, one from Intel, there's two problems with them. ARM or Intel, they're proprietary, so they wouldn't let us use them. That was one problem. The other problem was they were just too complicated. They'd be too hard to use. So we decided to start our own effort, and this was led by my colleague, Professor Krista Asanovich, and two star grad students, Yunsep Lee and Andrew Waterman, and I helped there. And then we had this interesting, and it took us a while to define that instruction set, but then we had this interesting thing happen. People from companies complain all the time about what you teach in computer science, but they were complaining that we were changing it in our classes. So why do you care what we do in our classes? And what we realized is there's this thirst for an open architecture. They didn't want to get a proprietary one. They wanted one that anybody could use. They wanted to use it in their products. And once we learned that idea, we thought that was a really great idea and wanted to make it happen. This is a really simple vocabulary. It's a clean slate design. So some of the RISC designs from 25 years ago had some bad decisions in them. We got to learn from that mistake. It's a modular. It's unusual for the vocabulary. You don't have to include all the words if you don't want to. And it can support these domain-specific architectures. But the biggest difference is it's an open foundation that runs it. So it started at Berkeley. There's a thing called the RISC-V Foundation. So there's a community that's evolving and running it, not just a single company. This is give you an example of the companies. It's been going on for 3 years. I think there's almost 200 members, mentioning a few. So these are two companies from China, and I think they are going to ship tens of millions of them sometime in 2019. NVIDIA announced that they're going to put all GPUs are going to have a RISC-V controller in it, so that's tens of millions. And then Western Digital, who makes these disk drives, they're going to put RISC-V cores in all the disk drives so that there'll be billions of them shipped every year. Okay. So wrapping up this talk, so what have you learned today? So 50 years of computer architecture. The first thing is this idea that software can inspire innovations. So the one idea was way back from the early 1960s is this idea of control is kind of like software called microprogramming. Another version is this open architectures idea. So from open source software to open architectures, so we're trying that to see how it works. That raising the level of abstraction can help with innovation. So the first was programming in languages like C++ instead of assembly language, led to RISC, and now we're having these domain-specific languages, and domain-specific architectures. So that lets us innovate below that and do things like the TPU that I showed you. And then finally, kind of sadly, it's the marketplace that's going to decide these things. The instruction sets computer architecture are closely tied with these research ideas, but the only way we've figured out how to settle debates is to get companies to spend billions of dollars when we try it in the marketplace. So an example that didn't work out so well was that the 432, that one, they went up to Oregon. The marketplace is not very patient. They were too late, and so the emergency replacement lasted forever, not the one that was intended to be designed. And then we're doing these studies right now. We're doing this competition right now about will it make sense to have open hardware as well as open source software? Can open hardware work? Well, the marketplace will let us know about that. And similarly, for these domain-specific architectures, particularly those for machine learning, where there's all this enthusiasm, big companies making big bets and different bets. Who's going to win that? We don't know. But I can tell you what is true is this is a very exciting time for computer designers. So that there's going to be brand new computers coming left and right, and we don't have Moore's law anymore. It's going to come from people designing these vocabularies and building the computers to make them better. And with that, I'm done. Can we do questions? Questions okay? Anybody courageous enough to ask a question? Yeah. Say that again. So RISC-V is actually pretty close to RISC-1. There's about 50 instructions in RISC-V. It's a modular design, so that's the base, and then you can add depending what you need. So if you need floating point, you can add that. If you need atomic instructions, you add that. If you add everything up, it's about 150, but that's much smaller. Does it typically do one instruction per clock cycle? And modern microprocessors, that's kind of a pedestrian way to do it. Yes, they could certainly do that, but often they try to do even multiple instructions per clock cycle, and it works that way too. There was very detailed questions. All right. Other questions? How to be successful? Yes?
So I have a question on the role of software in computer architecture and improving latency and improving performance for memory semiconductors, especially for supercomputers and such as like high bandwidth memory. What kind of future do you see in this space, like for memory?
Yeah, so memory is memory's like in your calculator when you remember something and bring it back, and it's vital for computing. It's a building block. Just like Moore's law is ending, there's been a technology that we've been using for 40 years that's coming to an end, and that's what's called DRAM, dynamic random access memory. We kind of don't know how to build the next generation. The current generation, which has 16 billion bits on it, it doesn't look like we're going to be able to build a 32 billion bit one. So what that means is this very important technology comes to an end. There's a half a dozen different technologies that people are working on to try and be that replacement. It's hard. In my career, there's only been a couple of technologies that have come in. Lots of them get advertising. Only a couple of them really worked. So in my career, we used to have magnetic core memories, and that became this DRAM. And another technology that works is flash memory that we have in all our phones and things like that. But there have been dozens of memory technologies that people are very excited about that never worked. There's about 6 of them right now that all look promising in the lab, but the hard part is you have to make them by the billions. You have to be, it can't cost too much. You have to compete, and DRAM is a high mark. So there's opportunities for new memory technologies, and there's a need for new memory technologies, but you be cautious. Computer designers are going to be cautious before they bet their computers on those designs until they prove themselves. Yeah.
learning, DSA instructor, like for machine learning, have in common with RISC-V?
So what it has in common in RISC-V is kind of, it's kind of a subtle argument, is there's going to be a lot of software that you're going to have to run. And there's typically the intelligent part tends to be a small part of the software. The part that adds the machine learning piece of it tends to be pretty small, surprisingly. So what you need is you need a computer that can run all of that stuff, and then you need to be able to interface efficiently to the special purpose architecture, the DSA. So RISC-V will be great for the big legacy code. And then people are looking at how extensions that would be good for machine learning. But that's this wide open area. So all we need to do in RISC-V is make it easy to add these instructions, and that's what we're doing.
So we had a talk about quantum computing today. So how does this compare to quantum computing? And will quantum computing somehow replaces all of these listed in the three?
Yeah. So the other question I get is the singularity for ML. So quantum computing is like fusion reaction, right? Fusion reactors. If fusion reactors work, that'll be a huge boon for humanity. People have been working on them for a long time, and they're not 10 years. They're at least 10 years away. Quantum is like that. It's a very exciting technology, but one of my former Berkeley student is in charge of a group that went to Washington where they had a meeting on quantum computing, and he asked them, is there a scenario that within 10 years some quantum computer will calculate something faster than a regular computer that anybody cares about? And nobody could come up with a scenario. So it's really at least 10 years away. Now, and then if it does work, we're not going to have quantum cell phones, okay? This is like giant mainframe computers that are in data centers. But, it's not, it's an exciting thing to work on. It's an open research topic. It's going to be at least 10 years. Companies are making investments, so that they're promising, but it's a long, Microsoft, Google, IBM, many companies, big companies are making investments, so it's not pie in the sky, but, that's happened before, and it's not necessarily going to work out. So and for 10 years we need some other solution. Okay, I think that's it. All right, thanks very much.